Hi friends, today we discuss about the charging and discharging of a capacitor through a resistor. The charging and discharging of a capacitor through a resistor is a classic topic in basic electrical and electronic circuits. It demonstrates how capacitors store and release energy over time when connected to a DC voltage source through a resistor. When a capacitor charges or discharges through a resistor, it does so exponentially with a rate determined by the time constant in RC circuit. The time constant is the product of the resistance and capacitance. During charging, the capacitor stores charge, and during discharging, it releases charge. The current, voltage, and charge on the capacitor all vary exponentially with time. Consider a circuit having a capacitance C and a resistance R, which are joined in series with a battery of electromotive force E through a key K. Simply, this is a classic RC or resistor capacitor circuit used to study the charging and discharging of a capacitor through a resistor. The image shown a simple RC circuit which includes a resistor R, a capacitor C, a battery epsilon and a switch K, where R means resistor, limits the flow of current in the circuit. C means capacitor, stores electrical energy by accumulating charge. Epsilon means battery, provides the electrical energy to drive the current. K means switch, controls the flow of current by opening or closing the circuit. First of all, we discuss about the charging of a capacitor. When a capacitor is charged, it accumulates electric charge typically by connecting its plates to a voltage source. This process involves the transfer of charge, with electrons moving from one plate to the other, creating an electric field and storing energy. The charge accumulation continues until the voltage across the capacitor plates equals the source voltage. When the key is pressed, the capacitor begins to store charge if at any time during charging. I is the current through the circuit and Q is the charge on the capacitor. In an electrical circuit, pressing a key or switch essentially completes the circuit, allowing electricity to flow. It acts like a gatekeeper, connecting the circuit and allowing current to pass through. The key in this context acts as a switch controlling the flow of electrical current. When a voltage is applied across a capacitor, it begins to store electric charge. This process known as charging, occurs gradually as charges accumulate on the capacitor's plate. The rate at which the capacitor stores charge is influenced by the circuit's resistance and the capacitor's capacitance, which together determine the time constant. If at any time during charging the current through in the circuit I and charge on the capacitor is Q, potential difference across the resistor V equals to IR. This is the equation number 1. It means the potential difference voltage across a resistor is indeed calculated using the formula V equals to IR, where V is the potential difference, I is the current flowing through the resistor, and R is the resistance of the resistor. This formula is a direct application of Ohm's law. Already we know the Ohm's law. Ohm's law states that the current I flowing through a conductor is directly proportional to the voltage V across it provided the temperature remains constant. Mathematical expression V equals to IR, where V equals to voltage measured in volts, I equals to current measured in amperes, R equals to resistance measured in ohms. Potential difference between the plates of the capacitor that equals to Q by T. This is the equation number 2, where V is the potential difference measured in volts. Q is the charge on the capacitor in coulombs, and C is the capacitance in farads. This relationship comes from the definition of capacitance, C that equals to Q by V. It means capacitance C is the amount of electric charge Q stored on the plates of capacitor per unit of potential difference V across the plates. In simple terms, capacitance tells you how much charge a capacitor can store for a given voltage. Since the sum of these potentials is equal to E, that is Ri plus Q by C equals to E. This is the equation number 3. This equation represents the loop rule from Kirchhoff's laws for a simple RC circuit, means resistor and capacitor in series with a voltage source, where Ri is the voltage drop across the resistor and R is resistance, I is current, where Q by C is the voltage across the capacitor, where Q is the charge on the capacitor and C is the capacitance, where E is the electromotive force or supplied voltage in the circuit. This equation assumes the components are connected in series and you are summing the potential difference around the loop, which must equal to the total supplied voltage E in accordance with Kirchhoff voltage law. As the current stops flowing when the capacitor is fully charged. When Q equals to Q naught, the maximum value of the charge on the capacitor, the current I that equals to 0. It means the current I initially is at its maximum because the voltage across the capacitor is 0 at the beginning. As the capacitor charges, the voltage across it increases, reducing the voltage and hence current across the resistor. Eventually, the capacitor reaches its maximum charge Q that equals to Q naught. The voltage across the capacitor equals the supply voltage. No potential difference remains across the resistor. Therefore, no current flows in the circuit, that is, I equals to 0. So, Q equals to Q naught. This is the equation number 4. I equals to 0. This is the equation number 5. This represents the steady state of a charging capacitor in a DC circuit. From 3, 4 and 5 equations, simply 4 and 5 equations substitute in the equation number 3. We get R into I means 0 plus Q means Q naught divided by C that equals to E. R into 0 plus Q naught by C that equals to E. Here R into 0 that equals to 0. Finally, we get Q naught by C that equals to E. This is the equation number 6. From equations 3 and 6, simply E value substitute in the equation number 3. We get Ri plus Q by C equals to E mean Q naught by C. Finally, Ri plus Q by C equals to Q naught by C, where R is the resistance, I is the current, Q is the charge at time t, Q naught is the maximum charge, and C is the capacitance. Rearrange it to Ri on one side. Simply, Q by C converts to the right hand side means minus Q by C. we get Q naught by C minus Q by C equals to Ri. Combine the terms on the left hand side. Q naught minus Q by C that equals to Ri. Divide both sides by R. We get Q naught minus Q by CR that equals to Ri by R, where R and R cancel in the right hand side. We get Q naught minus Q by CR that equals to I. This is the equation number 7. We know I equals to dq by dt. This is the equation number 8. This equation expresses current I as the rate of change of charge Q with respect to time t, where I means current measured in amperes. Q means charge measured in coulombs. T means time measured in seconds. From equation 7 and 8, it means the current I value substitute in the equation number 7. We get Q naught minus Q by CR that equals to I means dq by dt. Finally, Q naught minus Q by CR that equals to dq by dt. Rearranged the above equation to form a separable differential equation. We get dq by Q naught minus Q that equals to dt by CR. This is the equation number 9, where Q naught represents the maximum charge. Q represents the charge at time t. C represents the capacitance. R represents the resistance. T represents the time. Next, we see the step-by-step integration. When t equals to 0, q equals to 0, it signifies that at the initial time t equals to 0, the charge q is also 0. When t equals to t, q equals to q, it signifies that at the time t equals to t, the charge q is maximum. Integrating on both sides within proper limits in the equation number 9, we get integral 0 to q dq by q naught minus q that equals to integral 0 to t dt by CR. We know the formula integral dx by x that equals to log x. So, integral dq by q naught minus q that equals to minus log Q naught minus Q. So, integral dq by Q naught minus Q, that equals to minus log Q naught minus Q. Here, minus log Q naught minus Q limits 0 to Q, that equals to 1 by CR integral 0 to T dt, where integral dt means T. We get minus log Q naught minus Q 0 to Q, that equals to 1 by CR T in 0 to T. We apply the limits minus log Q naught minus Q plus log Q naught, that equals to 1 by CR into T. Rearrange the equation, we get simply multiply the minus sign on both sides. Log Q naught minus Q minus log Q naught, that equals to minus T by CR. We know the formula log A minus log B, that equals to log A by B. So, log Q naught minus Q minus log Q naught, that equals to log Q naught minus Q by Q naught. We get log Q naught minus Q by Q naught, that equals to minus T by CR. This equation relates the charge on the capacitor Q to time t using natural logarithms. Exponentiate both sides to remove the natural log. We get Q naught minus Q by Q naught, that equals to e power minus T by CR. This isolates the ratio on the left hand side multiplied both sides by Q naught. We get Q naught into Q naught minus Q naught by Q naught, that equals to Q naught e power minus T by CR. Here Q naught and Q naught cancelled in the left hand side. We get Q naught minus Q, that equals to Q naught into e power minus T by CR. Now you have an expression for how much charge is still missing from the capacitor. Rearrange to solve for Q. It means Q equals to Q naught minus Q naught into e power minus T by CR. Factor out Q naught. We get Q equals to Q naught into 1 minus e power minus T by CR. This is the equation number 10. This gives the standard form of the capacitor charging equation. We know the formula tau equals to CR. This is the equation number 11. This is known as the time constant, denoted by the Greek letter tau of an RC circuit, where C represents the capacitance measured in farads, R represents the resistance measured in ohms, tau equals to CR represents the time constant measured in seconds. The time constant tau tells us how fast the capacitor charging or discharging. From equations 10 and 11, it means CR replaced by tau. We get Q equals to Q naught into 1 minus e power minus t by tau. This is the equation number 12. The above equation gives us the value of charge on the capacitor at any time during charging, where Q represents the charge on the capacitor at time t. Q naught represents the maximum charge, the capacitor. Tau represents the time constant of the RC circuit. E represents the Euler's number, approximate value 2.718. Next, we discuss about the time constant. The dimensions of CR are those of time. It means the product of capacitance C and resistance R in a circuit denoted as CR has dimensions of time. This is because capacitance is measured in farads and resistance is measured in ohms. And the product of these units results in a unit of time, typically seconds. If CR double less than 1, Q will attain its final value rapidly. It means the time constant is small, the system responds quickly, and Q reaches its final value rapidly. If CR double greater than 1, Q will attain its final value slowly. The time constant is large, the system responds slowly, and Q reaches its final value slowly. Thus, CR determines the rate at which the capacitor charges or discharges itself through a resistance. It is for this reason that the quantity CR is called the time constant, or more appropriately, the capacitive time constant of the circuit. In a circuit containing a resistor R and a capacitor C, the capacitor's charging and discharging behavior is governed by the RC time constant. The RC time constant is a crucial parameter because it dictates how quickly the capacitor reaches its steady state value during charging or discharges back to zero during discharging. In simple terms, the time constant tau equals to CR is a fundamental in controlling how fast or slow the voltage or current charges in an RC circuit. If T equals to tau, this is the equation number 13. From equations 12 and 13, simply t value substitute in the equation number 12. We get q equals to q naught 1 minus e power minus t by t, where numerator tau and denominator tau cancelled. We get q equals to q naught 1 minus e power minus 1, where e power minus 1, this is a fundamental identity from exponential mathematics. The negative exponent means reciprocal. So, e power minus 1, that equals to 1 by e. We get q equals to q naught into 1 minus 1 by e, where e represents the Euler's number or the natural exponential, is a fundamental mathematical constant approximately equals to 2.718. So, E equals to 2.718 value, substitute to the above equation. We get Q equals to Q naught into 1 minus 1 by 2.718, where 1 by 2.718 means the value 0.368. So, Q equals to Q naught into 1 minus 0.368, where 1 minus 0.368, that equals to 0.632. So, Q equals to Q naught 0.632. It means Q equals to 0.632 Q naught. Simply, the Q value 63.2% of Q naught. Time constant of a CR circuit is thus the time during which the charge on the capacitor becomes 63.2% of its maximum value. In simple terms, the time constant of a RC circuit is the time during which the voltage across the capacitor or its charge reaches approximately 63.2% of its final or maximum value during charging.